Without further ado, I'd like to turn it over to Dr. Jonathan Speed. Jonathan?
Thank you. Thank you very much for the introduction and for the opportunity to speak to everyone here today. So the purpose of this, as outlined, hopefully there's something here, whether you work in a pulp mill, a paper mill, or actually any industry really. I'm going to give a brief overview of spectroscopy conceptually and the techniques that are involved there, and then give some examples in, as we say, the recovery boiler and also about stickies. So the first thing to note is that we are actually in the midway through the fourth industrial revolution. So the first industrial revolution was in the late 18th century, and this was actually using machines to start doing some of the work for us. Then came the second industrial revolution, and this was mass production, electricity, division of labor, Henry Ford's production line, that kind of thing. Then the digital revolution came in the second half of the 20th century. This was all about automation, electronics, and the beginning to use IT to actually start to automate processes for us. And we are now running through the fourth industrial revolution. The title Industry 4.0 is what people like to refer to it. And this is all about cyber-physical systems, digitalization, big data, actually being able to make decisions on the fly, but completely by automation and by artificial intelligence. And the idea here being that humans can step back from the day-to-day running of processes and get more involved in the top level strategic, the checking of things, but not the day-to-day kind of pulling of levers and turning of dials. And it's a really interesting time to be involved in spectroscopy and in other sectors. And I'd like you to bear that in mind as we go through this webinar and talk about various aspects. The key thing, and there's a famous quote by Lord Kelvin, that which cannot be measured cannot be controlled. So how do you actually make these changes and start to implement Industry 4.0 if you're not able to make the measurements that need to feed into that? So what kind of measurements are available? On the left-hand side of this, we've got simple online measurements, things like pH, temperature. We've been making those measurements for hundreds of years. And pH probes have been around for decades, temperature probes, likewise. They're very simple. They measure one thing. The pH probe actually measures electrical potential. It's a voltage. Temperature probes, very often they're a voltage as well. But they're measuring one thing and then converting it to the measurement you care about, which allows you to infer what's going on. And in pulp making, for example, you're probably going to get pH 14. That's pretty much all you're going to get, certainly online anyway. Temperature, that can fluctuate, but that doesn't tell you what's happening at the chemical level. It just tells you that you're at a certain temperature, which is really important and the kind of measurement we should make, but it only gives you a small amount of information. On the right-hand side of this image, we have offline measurements. So you may have come across HPLC, that's not so much used in pulp and paper making, but it is a technique. Auto titrators would fall under here as well, or even just benchtop titration, where you're taking something offline and you're measuring it. Now, an auto titrator sounds like it's online, but it's not. It's an auto sampler and an offline piece of kit. They're great, but it's offline. You're physically taking a sample to the instrument and processing it. That allows you to directly monitor the concentrations that you care about, but they're not in real time. They are often quite expensive and they can be very slow. So at one extreme, we've got fast measurements, but not very informative. And at the other end, we've got informative, but slow. Spectroscopy bridges that gap. Spectroscopy makes a direct measurement of chemicals that are present. It does actually look at the chemicals themselves rather than the properties. But you do need a calibration for it, and you do need to pick the right technology and the right spectroscopy for your process. I'm going to go into a little bit more detail about what those are in a minute, but not all spectroscopies are the same and they look at different things. So it is important to pick the right one. So in terms of online measurements, just to go into a little bit more detail here, there are quite a few here. We've got capacitive measurements, refractometers, optical density, temperature probes, pH probes, dissolved oxygen, ion-specific electrodes, or molecule-specific sensors. This is not exhaustive. There may well be some others, but this is a relatively good kind of breakdown. And you can see on the left, we've got inferential measurements. So they are measuring fundamental properties, sorry, but they're not measuring chemicals. In the middle, well, off to the left, at the middle of the left, if that makes sense, we've got our refractometer and optical density. They are light-based measurements, but they're not what I would call full-on spectroscopy. They're single wavelength measurements. Then on the right-hand side, we have processes that need membranes because they only allow certain things to go through. Even a pH probe is actually a membrane. It's just a glass membrane. And then we've got electrochemical measurements as well. So the way that these work are all differing degrees of complexity, but they all, again, all they ever do is they measure a property, apart from the far right-hand side that are molecule specific, but those are very easy to foul, and they don't really work in the pulp and paper sector. So lots of different technologies that are out there, and they're all important in their own way. And if I were building a brand new mill today, I would put at least half of these in because they are incredibly valuable and they do give you information that you need, but they don't give you the level of information to make detailed decisions. Offline gives you that level of information. So we've got chemical assays on the left. That's something like a lab-based titration. So, old school, a burette and a conical flask, and you add an indicator and you titrate until you get to the right number. You can get instrumentation that does that for you. So that's where the overlap there is, like an auto titrator. And then on the right-hand side, we have things like chromatography. So if you wanted to take a sample from a paper machine and you wanted to find out all the different organic molecules that might be present in that have come off from glues, inks, dyes, various other things that might have come in on OCC, chromatography will split those out for you, and then mass spectrometry, which could be the instrumentation there, might let you know what those are. But that is a huge amount of work. It needs dilution, reference standards, and it probably needs a skilled technician. So very, very informative, but not the kind of measurement that you're going to be wanting to use regularly to make routine process adjustments on. So spectroscopy. Some of you may be very familiar with spectroscopy and may have come across it many times before. Some people may have never heard of it at all and would like to go through the fundamentals. So I'm going to do that just in case. Effectively, fundamental spectroscopy is incoming light. So that's our kind of V1 light comes in and outgoing light leaves. So light comes in, something happens to it, and light goes out. And you can see the color has changed. So in this example, I've got red light coming in and orange light going out. Spectroscopy is defined as the interaction with light and matter. So if you look around you, in whatever room you're in today, you'll see various items of different colors. But the light in the room you're in is probably a white light. Now, white light doesn't really exist. It's a cluster of different wavelengths. So we've got the same size light, same colors of light, shining on everything in the room, but they all look different. And that's because the molecules that make up the table, the chair, the wall, the paint, is interacting with the light from your light bulb and reflecting different colors back to you. That is, in its most simple form, spectroscopy. What spectroscopic instruments that you do is actually turn that into full-on information, into numbers that can then be turned into concentration profiles. And we use a huge different number of wavelengths of light. So this is a picture of the electromagnetic spectrum in front of us now. And we can see on the left-hand side, we've got radio waves that are very, very long wavelengths, very low energy. And on the far right-hand side, we have gamma rays, very short wavelengths, very high energy. The typical wavelengths that we use for spectroscopy are ultraviolet, visible, infrared. There are spectroscopic techniques built on microwaves, but they're not very common. And radio wave-based spectroscopies are things like MRI instruments in a hospital. That's based on radio wave spectroscopy. There are chemical versions of this. They're called NMR machines, nuclear magnetic resonance, but they're not really designed for online use and for processes. They're fantastic for laboratory studies, but they're not great for day-to-day. There are some new instruments coming onto the market that are effectively auto samplers coupled up to them, and for very niche applications, they're really powerful. But for the day-to-day, I wouldn't advise using one. Here is a table of different types of spectroscopy. So we've got fluorescence as the top row. This is incredibly sensitive. Fluorescence typically uses ultraviolet and visible light, but it's very niche. It only works for a few select applications. So if you have an application where fluorescence works, it's very powerful. But there are many applications where it doesn't work. So it's either going to work or it doesn't. And unfortunately, most of the time, it's not useful. Raman, which is the next one down, is a type of, it's halfway between an infrared and a fluorescent spectroscopy. It's very information rich. There's a lot of information there, but because of this fluorescence issue, fluorescence can be a challenge with it. And it doesn't tend to work well when you have particles. So fibers in a fiber line, for example, Raman is probably not going to give you what you want to measure there. Near infrared is something that you may have come across. There are near infrared instruments in the pulp and paper manufacturing space. And that's because near infrared has been around for a few decades now in manufacturing. And for applications where it works quite well. But there are many applications where near infrared doesn't work because the level of information there is quite poor. Near infrared is to mid infrared what looking at someone's silhouette is compared to looking directly at their face. You get a rough idea of who they are, and if you know them very well, you'll probably recognize them. But if you've never met them before, you won't have a clue what they look like. And near infrared is quite similar. It's not very rich in information. So trying to differentiate molecules that are quite similar, like a sulfate and a sulfite, near infrared can't really do that very well. Whereas mid infrared can. So mid infrared gives you much more information. But the problem is traditional mid infrared instruments are very fragile and they're not really suitable for the manufacturing space. The instrument I'm going to talk about today has overcome that. It's the static optics FTIR you can see at the bottom, and I'll come on to that in a second. But mid infrared, very information rich, traditionally very fragile. Near infrared, information poor, traditionally quite robust. So unfortunately, you don't get either that you want with those two techniques. UV vis, so ultraviolet and visible light, they're actually stuck together. We call it UV vis. That package of wavelengths always comes together. Again, it's a bit like fluorescence. So when those samples work well, it works really well when that kind of application, but it doesn't work very well for most things. It's quite niche. It's very good for metals. So if you look at a firework burning, the color that you're seeing is effectively UV vis spectroscopy. So if you want to see the amount of copper that's present in something, UVV does a great job. But if you want to see organic molecules or inorganic molecules that aren't metals, UVV doesn't really do a very good job there. And then nuclear magnetic resonance, NMR, the one I mentioned previously, it's inherently quantitative, which is fantastic, but it's not really online. It doesn't work for many applications, and you often need to use quite expensive deuterated solvents, so slightly radioactive solvents. They're not scary or dangerous, but they can be quite expensive in the long run. And then at the bottom, this static optics FTIR, and I'll talk about that, I'll talk about that today. It is mid-infrared wavelengths. So it's the same level of information that we get from a traditional mid-infrared or FTIR spectrometer, but there's no moving parts, which means the spectrometer is inherently robust and you can hit it with a hammer and it doesn't care. As an aside, FTIR stands for Fourier Transform Infrared, and that's the way that we actually turn light into information. All of these techniques I've laid out here need a way of turning a package of light, of wavelengths of light, into information. The most obvious way is a prism. You've probably seen the famous album cover with a prism on. White light comes in, the split light comes out. That's one way. Gratings are a bit like a prism, but flat and small. If you look at the back of a CD or a DVD, that's effectively a grating. You can see that rainbow pattern. And Fourier transform is the other way. So those are broadly the main three ways of creating turning light into information. Just to go through a little bit more detail about spectroscopy, in this case, these are the type of energy transitions that we see when we're looking at spectroscopy. So on the left-hand side, I've got UV vis. And I appreciate this slide is a little bit quantum mechanics. It's a little bit complicated, but just to take you through it. All molecules start off in this ground state, we call it. So think about walking up and down some stairs. You start at the bottom, you start in your ground state. If we put in UV vis energy, because it's a shorter wavelength and it's highly energizing, the whole molecule actually jumps up to an excited electron state. That's what that's called. And that gap, that energy gap, corresponds to UV visible light. So that's what we're seeing. And this happens a lot in metals and in some organic molecules. They tend to be brightly colored. So carotene, for example, it's a bright orangey yellow color. That undergoes this transition, which makes sense because it's UV visible light. So that explains why carrots have a color. the electrons are jumping up to that energy level. We have the same thing going on for mid-infrared, but instead of electrons in the molecule moving around, it's actually the vibrations of the molecules. Molecules are not static blobs. They are constantly vibrating. All chemical bonds are constantly vibrating and rotating and moving around. They're not stationary at all. They are constantly moving. And a mid-infrared transition corresponds to kicking more energy into that and speeding them up and making them move even faster and jumping up an energy level. So you can see it's the same fundamental concept. We go from ground to up one level for UV vis. We're doing the same thing, but we're doing it in the next set of rungs. It's a smaller rung to jump up, but that's all mid-infrared is. Near infrared is a combination of the two. It's kind of halfway between them. So rather than jumping up one rung, which is what you do with mid-infrared, and it's therefore easy to interpret what's happened, with near-infrared, you jump up multiple rungs. So if you're moving up more than one rung for one particular vibration, that's called an overtone. Or you might be moving one vibration and another one up one rung at the same time, and that's called a combination band. And they're very complicated to unpick what's going on because you're not looking at fundamentals. And that is where that difference in information comes from. On the right, we've got what are called Rayleigh and Raman. So Rayleigh scattering is no change whatsoever. You'll notice that arrow goes up to a virtual energy state, and then it drops back down again, and it ends up where it was to start with. So there is no change. And this is actually related to why the sky goes different colors during sunset and sunrise. It's Rayleigh scattering of particles. You'll notice that there is no change there. So light gets scattered based on its wavelength, but the energy remains the same. A Raman transition is slightly different. In this case, the molecule goes up to this excited virtual state. It doesn't really exist. And it drops back down again onto a different rung. And I apologize, there's a slight mistake there. That arrow should be at that rung in the same way that the MIR one is. And you'll notice it lands to the same place. So it's the same information that we're looking at with mid-infrared, but we get there in a different way. Now, there are some things called selection rules, and exactly what type of vibration we can see in a molecule changes, whether it's mid-infrared or Raman. That's beyond the scope of this webinar. I'd be more than happy to explain that to people in more detail if they'd like me to later on, or in separate phone calls or whatever. But there are differences. It's to do with quantum mechanics and the way electrons move around the molecule. But they are slightly different. So it's the same type of information, but exactly which bit we get are different. So just to go into a bit more interest on the near infrared and the mid infrared, as I mentioned, combination and overtones, they're much harder to identify than the fundamentals. And near infrared struggles to differentiate between similar molecules. So the example I like to use here, a bit like the silhouette one, is this a vase or are these two faces? You can't tell from this picture. It's a vase. So with mid-infrared and FTIR, this is the kind of level of information we get. With near-infrared, we can't quite tell. The other thing that's worth knowing is that mid-infrared instruments are based on what's called ATR, attenuated total reflectance. And on the left-hand side of this picture, we can see that. So we have solids, bubbles, but we don't really care because there is this evanescent wave. That's where the sensing happens. And that's measuring the liquid. And a solid might bump into it and move out, and a bubble might do the same. But over time, this averages out, and we can remove that using some simple maths. Near-infrared probes are based on reflectance. They're either a transmission or reflectance, or sometimes they're called transflectance. But effectively, you have a light path that's about 1 centimeter. And in that case, in theory, they work great. Mirrored surface, light goes off, bounces off them, comes back in again, make your measurement. But in practice, when you have a bubble or a particle, they start to change the length of that path beam, and it becomes chaotic and it becomes very difficult to use the instrument. And if anyone here has tried to use a near-infrared instrument, particularly in pulp making, and has struggled, this is potentially why. So how do we actually use it? We have to acquire calibration spectra and a calibration reference concentrations. And we put the two together to make a regression model. It's a regression model in many dimensions, but it is a regression model. The golden rule stands of garbage in, garbage out. So if we feed in bad quality lab data, we get a bad quality lab calibration. If we feed in good quality data, we probably get a good quality calibration. And then what we do is we then use that model and we validate it during use. And effectively what it says is, if you had taken that sample to your lab, this is the measurement you would have had, which is incredibly powerful, being able to make that every minute, every 2 minutes, every minute of every day, continuously. So stepping back slightly, who is Keit? Who are we? That was the foundations, just to give you a very quick overview of who we are. We're in the UK. There's a little map that shows you where we are. We're a spin out from a government research lab. And the key thing about what we've got is there was a spectrometer that was developed to go to Mars. And if you want to send something to Mars, it's got to be simple, it's got to be robust and rugged, and it's got to not need a service engineer to come and visit it all the time. And we were then set up to take that technology and turn it into something for the UK, for the Earth, rather than for space, that could be used in industry. And that's the fundamental principle of the static optics spectrometer, which is here. So the way this works, this is a relatively simple drawing. We start at the light emitter, and light is created by that, and it goes down the end of our probe and into this ATR that I mentioned. And the ATR interacts with the liquid, and light absorption happens. That's where the actual spectroscopy happens. That light then ends up back into the body of the spectrometer, and it hits what's called a beam splitter. Half the light, the red dashed lines, goes straight through and goes round this track of mirrors and hits our detector. The other half of the light is reflected off the beam splitter, goes the other way around the track of mirrors, gets reflected again, and hits the detector. And these two beams of light hit the detector slightly offset from each other. And that creates an interference pattern. You may remember the young slits experiments from high school. It's the same thing. And this interference pattern gets fed into Fourier transform. That's where the FT in FTIR comes from, and turned into a spectrum. And that's how we take a packet of light, of different bundles of wavelengths of light, and turn that into information. What's beautiful about this is because everything is bolted down, it can shake, it can vibrate, it doesn't care, and you get a spectrum all the time, whereas traditional instruments have moving parts, which means if you have any vibration going on, the whole thing stops working. That's a picture of it. It's about 24 centimeters wide, 30 centimeters long. It's got an armored shell and a sensing probe. And we thought, what else looks a bit like that? And we realized it's an armadillo. So the instrument's called the IRmadillo. You've got to have a pun based on infrared nowadays. So IR for infrared, IRmadillo. Hopefully at least some of you are smiling at that. So let's talk about the exciting stuff, reduction efficiency. So we did some work with a mill in Sweden who wanted to look at reduction efficiency in their green liquor. So the outlet of the smelt dissolving tank, they wanted to be able to measure what was going on and feed that back to control the boiler. And these are the results from our lab testing. So quite rightly, the first thing they said is, we would like to send you some samples and you analyze them in the laboratory. If that works, we can then progressively move this project forwards. So that was what we did. So we've got effective alkali, sodium hydroxide, sodium carbonate, sodium sulfide, sodium sulfate, and sulfur levels on this graph. And you can see on the right, we've got our average errors for these calibrations. These are all chemometric calibrations. So we take the whole spectrum and we correlate that to the known reference values. And we then do a cross-validation where we take samples out, we rebuild it, test them, take a different one out, rebuild it, test it. And that's what these numbers are here. So for example, sodium hydroxide, we've measured from 3 to just below 6, plus or minus 0.2. So based off these numbers, the customer was happy to move forwards and to actually take an instrument and install it online. So that's what the photograph here is. So this is the instrument with a welded flange. So it's actually, the flange is welded onto the probe to make sure there are no leaks. That goes into a T-piece in their smelt dissolving tank outlet, and we're measuring constantly. They flush the line with weak green liquor, and that cleans out the pipes and prevents scaling. And we then calibrated that with online process data that was then taken to the lab to get us reference data. And here are the results. So the red dots show the laboratory reference data, and the black line shows our measurements. Now, obviously, you can see that, for example, if we look at the sodium sulfate, the lines periodically drop down. That's when the green liquor, the weak green liquor, was in to flush the line. So obviously you should only pay attention to the numbers that are actually on the graph here. But you can see we've got very good correlation there. They take multiple samples throughout a process run that we've built these correlations against. And by taking the sodium sulfide model and the sodium sulfate model, we can then calculate reduction efficiency. And their target is they'd like to be at 95% or above all the time. And they're not quite there yet. They've had a couple of good days, but with this information, they can now start to drive the process, and they are already doing so. So they bought the instrument from us following this trial, and they're now looking at changing the flow of air, the flow of steam, the flow of everything to start to optimize this. They're currently doing it manually and doing experiments. And once they've done that and they've understood what levers to pull and how they change things, they plan to then build an automated process that will take this measurement, feed that into their control scheme, and that will automatically adjust the valves so that they can constantly run at the highest efficiency possible. I'm really excited by this, and I think it's a fantastic implementation that they've come up with. They're also looking at what else they can do with this. Can they use this to then feed forwards and look at things like TTA value, and then measure that so that they prevent overliming? So it's a really clever way of using one installation to look both backwards at reduction efficiency and forwards at recosticizing. Another quick one here, extractives in black liquor. So black liquor, we have they call it Extractives. This is a different mill in Sweden where they've got tall oil, resin acids, unsaponifiables, various different things that are present that they don't really want to burn. They want to extract those and sell them on to tall oil refiners. But at the moment, they're accidentally feeding them through to the boiler. So they want to be able to measure what's there and then change the settling so that they can remove it. So that's what we looked at. And in this case, we are looking at a huge number of different molecules in one go. It's not just one molecule, it's lots. So this is actually based on multiple different spectra, all interwoven with each other. So it's a multi-dimensional calibration. But you can see here, we're able to pull this out. R squared of 0.964 and an average error of 1.35 over a range of just above 2 up to 30. So we're pretty happy with that. And off the back of this, the customer has bought an instrument to install online to be able to control this. And in fact, a second instrument to look at white and green liquor as well. So it's really exciting time to be working with the pulp mills here, because I can see this potentially changing the face of chemical recovery. And it's one instrument that can measure pretty much anything, which is fantastic. But one thing to bear in mind is not all extractives are the same. We've got polar extractives and non-polar extractives. So you've got variations of that. As if we look at a fatty acid, for example, a fatty acid with 8 carbons is going to be much more water soluble than a fatty acid with 20 carbons. And the polarity changes throughout that. And I'm not allowed to go into too much detail because of potential patent filings, but we've developed a technology here that allows us to split them out without necessarily needing huge amounts of mass spectrometry or HPLC or anything else. And by using that approach, you can see here that we've split them. So we've got the total dissolved extractives on the x-axis here that the customer reported as, yes, when we dried these, this is how much stuff was left. But you can see we've got the red and the black where we're actually able to differentiate between them. This is really important for pulling out more hydrophobic molecules. So how does this actually help with stickies, which is the other thing I said that I was going to talk about today? Well, stickies are just extractives in a paper machine, really. Extractives in pulp are organic molecules that they don't really want in there, that if they end up on the fiber can cause spots and colors, or if they end up in the black liquor can be burnt when they want to extract them. They are, on the most part, hydrophobic molecules. So on the left, we've got hydrophobic. It's a huge range of individual chemical species. It's not just one. They're dynamic. The concentrations are changing and the relative concentrations within them are changing. And it is almost impossible to quantify in the feedstock, because if you'd done it, if it was easy, you'd have already worked out how to do it. So they are, to all intents and purposes, certainly for the purpose of this, the same thing. So that means we can build a calibration for it. And this is something we could measure in a paper machine. And we are actively talking to customers now about moving this forwards and actually doing this installation. We haven't had a chance to do it yet. So if anyone on the call would like to talk to us, I'd be more than happy to listen. But we are beginning to move this forwards. So what do? The first thing you do is you install an instrument online and start collecting spectra. That's fairly simple, fairly easy to do. We've then got those spectra and we're just constantly measuring what happens. We can then take offline samples. And we could, at that point, try and calibrate for other species of interest. So, for example, ASA. I believe that some of the issues that some customers are having with gumming and stickies formation is actually the ratio of ASA to emulsifier might be changing. And if you know it's a specific molecule you're looking for, then HPLC or something similar is a way of measuring that. So we could then try and measure the amount of residual ASA, the amount of residual emulsifier, etc. And we could build a model for that in the same way that we've done for known extractives or for the chemicals in the green liquor for the pulp. So that's easy to do. That's not a problem. The other thing we can do is we can look for these hydrophobe levels. So we can actually take a spectrum and we can pull out the amount of hydrophobe that's there in the same way that I did in the slide graph a couple of slides ago, where we look at the amount of hydrophobic molecules. And that is effectively a way of looking for how much stickies are there, because hydrophobes and stickies are very strongly correlated. So if your hydrophobe level goes up, your stickies is almost certainly going up as well. So that's a model we can build. We actually need, we do need to take samples offline to do that, but it's not too difficult and it's fairly easy to do. So we can throw that calibration in at the same time. Bear in mind, you can run multiple calibrations at once. The other thing we can do with this online instrument is we can build PCA models, so principal component analysis, which I've not really gone into too much detail here, but a PCA model is effectively looking at trends and it's looking at the information within the spectrum. So we can look at that and you get that for free effectively because it's sat there running, and building a PCA model is relatively easy. So we can do that. That then pulls out information and we could see, oh, this thing is changing over time. You've got a buildup of something here. Or you've got a periodicity, did you know that? And that can feed in as well. And the last thing is what I call a camera trap. Now this one's a little bit rolling the dice, but effectively what you do is you wait for it to go wrong. So you wait for a break on the paper machine, or you wait for a buildup of stickies that causes a problem, or marks on the paper. And at that point, you mark in the spectrum and you say, I saw this problem at this point. And then we can actually use machine learning to go, oh, that problem correlates with this feature in the spectrum. The next time I see that feature starting to grow in, I'll give you an early warning so you can do something about it. And all of those things can feed into a take action model. And what's beautiful about spectrometers is you can always go backwards in time and look at what was happening earlier once you built your model. So it's possible to install a spectrometer fairly early, start measuring everything, and then go back and pull out huge amounts of information. And you can keep throwing on calibrations to get more and more out of one install. So I think it's a really exciting way of analyzing a process. And I'm hoping to come back to people in a year or so and present, and here is how we fix stickies. I appreciate that's throwing down the gauntlet, but why not? Let's try and make that happen. So in conclusion, spectroscopy, it's no longer a tool just for the lab. It was 20 years ago, 20, 30 years ago. It was a lab-based tool and it was really powerful. But nowadays it's finding its way online. It's a core part of Industry 4.0, and it's what's going to drive the change to automation, big data, and artificial intelligence-led processes. Spectroscopy is going to be a core part of that. And static optic spectroscopy is a viable route for measuring these chemicals, processes, and states in pulping and paper making and beyond, but I'm aware that the interest group here is principally pulp and paper. And I know this is a slightly crass way of saying it, but if you want to measure it, spectroscopy or some form or another, probably can. It's pretty much anything can be measured by spectroscopy nowadays. So if there is something that you wish you could measure, if you're sat there thinking, my life would be so much easier if I just knew this, there is probably a form of spectroscopy that can do that. And I'd be more than happy to try and answer that if there are any questions on that. So that's a whistle-stop tour through spectroscopy at the front end and some examples that I've got. I do hope that's been helpful and informative. And thank you for listening. That's my email, jonathan.speed@kite.co.uk, if you want to take any conversations offline, but I believe there is time for any online questions right now. And I'd be very pleased to answer those.
Thank you, Jonathan, for the presentation. At this time, we'd like to open the discussion up to any questions that the audience may have for the speaker. If you have any questions, please type them into the Q&A feature on the side of your screen now. We will pause for a few moments to allow you to do so. All righty. The first question I have is a bit lengthy, Jonathan, so just give me a moment to go ahead and recite it off. On the slide 17, you show very well-developed calibration curves for different compounds that we generally see in the black liquor and non-washed or partially washed pulp. Will the probe work in a mixture of pulp and black liquor suspension, for example?
So I'm just going to go back to slide 17 to make sure that we're all looking at the same one. I think it was probably around about here. So yes, is the answer. So this is the beauty of ATR, in that it doesn't really care about the solids. So pulp is not a problem. We've done some work in actually recycling of municipal solid waste, where there are very high solid loadings of partially shredded pulp and OCC and various other nasties. So that's not a problem. The solids aren't an issue. It does mean that we can't measure the solids. So if you're trying to measure the fiber itself, that's not something that our spectrometer would do a very good job of. But it does mean that measuring in pulp itself is not a problem if it's the liquids that you're trying to measure.
Alrighty, thank you. Next question. Can you pull out talc pitch agglomerations out of pulp streams?
That's an interesting one. An agglomeration, if it's a solid particle, effectively, if it's acting like a solid particle, that might be tricky to see. As I said, based on the answer about solids. If it's more like a sol gel, where it's moving and it's mobile and it's kind of this, it's almost like a liquid globule within a liquid stream, that might be something we could see. I don't know, is the short answer. It's the kind of thing that might be worth doing a proof of concept on in the laboratory, if that would be possible. Pitch obviously has a very different spectrum to a lot of the things we want to look at, because it's mostly hydrocarbons. So that's quite obvious. Talc is quite different, again, in a different way. So spectrally, we would be able to differentiate between them, but I don't know if the particle size would allow us to see it. Because the way the probe works is it sees things that are very close to it. So liquids fill the gaps so that they're really easy to see. Particles, as they're moving, it does depend on their morphology. And that's why things like fibers are not a problem. But the flip side is that means we might not be able to see it. So I don't know. It's something that, if there are samples that can be prepared, we should definitely have a look.
Thank you. Next question. Does the probe require any concentration, very low concentration, for example, for it to work properly?
No. So I know that one of the issues with things like certain titrators or offline analysis, HPLC, for example, requires dilution. And you do need to dilute things before you can actually analyze them, because you'll saturate. The beauty of this one is that we don't see saturation. It's because of the ATR. If it was a transmission probe, and you may have heard FTIR doesn't work in water. That's because transmission probes don't work in water. They do saturate. That would be a problem. But an ATR probe, which is the one we use, doesn't have that problem. The only time I have ever seen saturation was a very, very niche application with a particular solvent called NMP, N-methylpyrrolidone, that one particular part of the spectrum saturated, but the rest of it was fine. But that's the only time I've ever seen it, and nothing else ever saturates. So no, we don't need, it's designed to be fit and forget. So shove a flange where you want it, put the probe in, do it up and walk away. Because they're supposed to, if they're not easy to install, then they become difficult to service and difficult to work with. So no dilution required.
Thank you. Here's a two-part question. Do you have any issues with color? And could I do an install in white or black liquor?
So color's not a problem. Mid-infrared doesn't really see color. So if we were using a UV vis instrument, it would, because obviously that's visible light, we're looking at color. For us, we don't see the color, so it's not a problem. In some instances, in somewhere like the edible oil space, people actually want to measure color. And in that case, we do it by measuring the chemicals that cause color rather than color themselves. In pulping, it's not really a problem. Yeah, green or white liquor doesn't really matter either way. We've identified applications across in green, white, black, and if any of you have come across orange liquor, we've identified applications there as well. So yeah, wherever works for you based on the combination of how easy it will be to install and what you actually want to measure, it makes almost no difference.
Alrighty, and what about scaling up of the probe?
Yes, so if the probe window were to be completely covered in scale, that is potentially a problem. So the way that the ATR works is it needs to see the liquid. And very recently, actually, we had a customer who was reporting that it took a long time for their sample to stabilize. And they would flush out their line, and then it would take upwards of an hour before it would actually completely stabilize, which doesn't make sense. It should be within seconds. We looked into this and eventually found that the probe was coated in a millimeter or so thick layer of personite. So the first thing there, it doesn't completely stop working. It carries on working, but with this, this delay, which isn't helpful. We don't want the delay there. And the second thing is I then took that as, I can now build you a calibration that tells you when your probe is scaled. So I did that. And I actually went back and then reanalyzed the last month's worth of data. And I can tell them the minute their catastrophic scaling event happened. And it's also when they had a very high TTA value. So something in the process went wrong. They were using the spectrometer to observe, but not to control, and they got a scaling issue. And so it was a problem. It was very quickly removed with hydrochloric acid. It was easy to wash off, that's not a problem. And we were able to alert, you now need to do this. And part of what we want to install moving forwards for customers is this alert. It's effectively a 1 if the spectrometer is happy, it thinks it's measuring what it should be, there's no problem, and it flags up an alert and it gives you a 0 or the other way around, saying, I have a problem, you need to take action. And if it's a scale that we've seen before, we can actually flag that up as, I am now scaled, you need to take me out and clean me. This has happened once in a year for that spectrometer, so it's not a frequent event, but it is something that we need to be aware of. We are also working with a third party to actually implement in situ ultrasonic descaling, where the spectrometer has a descaler that focuses on the actual end of the probe itself and periodically blasts off any scale. So that would completely get rid of that problem altogether. So there are various options out there. So yes, in principle, it is a problem, but there are ways of dealing with it so that it doesn't become a game stopper, a show-stopping problem.
Okay, great, thank you. I have another question. How could I get offline reference data for Stickies to build this type of model?
Yes, so one way is to get a third-party lab. So we don't often try and suggest that we start with labs, but that might be, so a local university can help with something like mass spectrometry. That is one way of doing it. There are other slightly simpler ways. So for example, you can evaporate something down to dryness, see what was the total dissolved solids. You could do that and then wash away a chemical. So if for example, if you took an aqueous mixture, evaporated it to dryness in an oven, that then gives you a solid. You can measure how much is there. And then you could wash that with acetone, for example. That will dissolve away things that are soluble in acetone, and you can see how much of that is. So you'll be left with inorganic salts that won't dissolve in the acetone, and all your hydrophobic stuff will dissolve away. And that gives you a number that we could then use to feed in. So there are ways of doing it that don't necessarily involve a third-party lab, and you don't need very expensive equipment. It's all to do with the appetite for information and the appetite for cost. So if you're happy to spend some money and get lots of information, that's one way of doing it. If you'd rather do it as cheaply as possible, there are other ways of doing it. But as is always the way, the more money you spend, the more information you can get, but you don't have to spend large amounts of money to actually get something useful.
All righty, thank you. Let's see here. Next question. Do you have standard solution of sticky suspension in order for you to calibrate the instrument?
No, we've not tried that actually. It's that could be an interesting way to go. I mean, obviously the exact molecules that are present does change depending on your feedstock, probably changes over the course of a year. But that would be an interesting one to think about, creating this kind of standard mix. Not something we've thought of doing, but is a really interesting idea that I might nick.
Thank you. Great questions, everyone. We will pause for a brief moment to see if any other questions come through the chat or the Q&A features. So we'll pause here for just a moment. Alrighty, I don't see any other questions. So at this time, this will conclude the Q&A portion of the webinar. Thanks again, everyone, especially, of course, our presenter, Dr. Jonathan, and to Keit Spectrometers for today's presentation. As a reminder, a survey with a link to the webinar recording will be sent to all registrants later today. I encourage you to complete the survey so that we may get proper feedback on how to better serve you through these presentations in the future. Thank you, everyone, again for your time, and this concludes today's webinar. Have a wonderful day.